cominciamo. Scusa, io sto anch'io lì.
Una situazione anarco-insurrezionalista.
Io sto anch'io lì, poi vengo nel caso ci fosse bisogno, insomma, tanto. Allora, prendete posto per favore che cominciamo. La prima presentazione di oggi pomeriggio è di Enrico Piconcelli, The Bright End of the AGN Luminosity Function, the Realm of High Luminous and Highly Accreting Quasars.
Okay. Good afternoon. First of all, I want to thank the organizer for giving me this opportunity. I remember that I received the first invitation at the end of February 2020, where we are still happy, just a week before the lockdown. And so I'm very happy to be here in presence. So today I'm going to talk about the most luminous quasar, high luminous and accreting AGN at the bright end of the AGN luminosity function. So with high luminosity quasar, we mean an AGN with a bolometric luminosity larger than 10 to the 47 erg per second, which roughly correspond luminosity of 10 to 14 solar luminosity. And this is a comparison of different different luminosity function. As you can see that the brightest end of the AGN luminosity function is scarcely populated, and you can see also that basically you have to go to high redshift, in particular between redshift 1 and 3, to collect a number of this object. So there are the first two take-home message. The first one is the luminous AGN are very rare and distant. So this means that we need a wide area survey to collect them because due to their low surface density. And also it's still time consuming because they have faint fluxes. So for, in particular, spectroscopic follow-up, we need a very long and deep observation. And also another important aspect, you see that basically the peak, density peak of this object is cosmic noon, I mean between redshift 2 and 3. And so studying the high luminous quasar gives the opportunity of proving powerful AGN activity at the same epoch when the most of the most massive galaxies have collected most and formed most of their masses. In this talk, I'm trying to convince you why studying the most luminous quasar is a great thing. It's important to study this kind of object because you study the accretion disk corona and also other nuclear properties in the high luminosity regime, so a lot of radiation pressure emitted from this object, and also with a high accretion rate compared to lower luminosity AGN. And it's also important for the feedback because it's expected to be at its maximum level in this kind of object due to their very, very large luminosity. And so it's important to study this kind of object in the context of the coevolution because I show you that this kind of object is strictly linked to the evolution of the most massive galaxy. And also in studying high luminous AGN also means study the dark side of quasar, which means, this recently discovered population like a hot dust obscure galaxy on a red quasar, which represent a key phase of the quasar evolution sequence. So I start here with nuclear properties. I show a spectral energy distribution compared for different luminosity bin. The high luminosity objects are the blue one. And so the luminosity spectral energy distribution normalized here at 1.3 micron, and here in the near ultraviolet. So you can see that the high luminosity objects appear to have more hot dust emission, okay, with respect to their low luminosity counterpart, and also show a steeper far ultraviolet continuum. So for this plot, it's evident that there is no quasar, there is no universal quasar spectral energy distribution, and maybe there are some unseen component in the far ultraviolet component, in the far ultraviolet range, which is not observable. I strongly recommend to follow the talk by Vanu Sakeo, which is going to present some interesting results on this aspect. So when the accretion rate increase, are also expected to be to observe some change in the accretion disk properties. In particular, as you can see from a typical geometrically thin, optically thick accretion disk, the Shakura-Sunayev one, you can move with an increasing of the accretion disk to the so-called geometrically slim and optically thick accretion disk. Okay, so this is due to the fact that the radiation pressure increase and also the inner disk, the height increases, like the inner part of the disk puff ups due to the radiation pressure. In this case, I also expected to observe some change in the spectral energy distribution, like a boosted extreme ultraviolet emission, some deficit in infrared, and also maybe there are change in the energy transport from the accretion disk to X-ray corona, and also due to the fact that the accretion disk is thick, there are also change there are also occurring some X-ray view shielding due to the height of the accretion disk. Anyway, even if there is a lot of literature on the theoretical aspect of this change, the observational results and observational confirmation of this change are still scarce. So another important aspect of this slim disk is that its low radiation efficiency. Okay, and this is due to the advection and photon trapping, which is huge in case of this system. And you can see here, basically, this is the Eddington ratio, and this is the accretion rate normalized to the Eddington rate. And you can see that basically, even if there is a strong increase of 1 order of magnitude in the accretion rate, is expected to be only a very slow change in the volumetric luminosity. Okay, and I think this is an important aspect, in particular for the growing on the largest black hole at high redshift. So let's start with X-ray properties. This is a typical X-ray spectra of a type 1 AGN. As you can see in the soft part of the spectrum, there is a so-called soft excess component, and here the so-called warm absorber component due to the intervening ionized gas. So there's been early claims of weak and absent soft XRS and warm absorber in this high luminosity object, but they are not being confirmed by subsequent XM studies. Okay, and also the slope of the X-ray continuum seems to be constant around a value to 1.92 over X-ray luminosity, redshift, and Eddington ratio. So I strongly invite you to follow the talk by Marco Laurenti and Luca Zappacosta, which are going to present some interesting results on this aspect. So basically, in the soft X-ray and also the X-ray continuum seems to be the same, like in case of a low luminosity AGN CIFER galaxy. So what about the reprocessing feature? I mean, the iron canine and the Compton reflection amp due to the reflection of the Torus. So these some chains are being detected. In particular, this is a so-called X-ray Baldwin effect. And you can see there is an anti-correlation between the equivalent width of the iron K-half, or iron K 6.4 kV, and X-ray luminosity. And also seems to be a weakening of the reflection, the strength of the reflection continuum when you go to the high redshift. So there is a decrease of reprocessed X-ray emission from the torus with increasing luminosity. And this can be interpreted in terms of the so-called luminosity-regulated unification model for AGN, according to which the fraction type 2 object decreases with volumetric luminosity with a large add-into ratio. And this is basically due to the radiation pressure, which is able to sweep away the torus. So this is the first example of a radiative feedback shaping the closed supermassive black hole environment in case of a high luminosity object. So anyway, the situation could be a bit complex than expected. You can see that basically in the high luminosity part of this plot is populated by upper limit, okay? Because again, this means high redshift object, and this means faint fluxes, okay? So anyway, in some dedicated long observation, start to emerge a population of a very high luminosity object with the same reflection feature like in low luminosity AGN. And this, I think, is very interesting and deserves further investigation. So let's move to the feedback and to the coevolution between quasar and host galaxy. So this kind of luminosity, in case of high luminosity object, implies that the black hole at the center of this object is a billion solar masses, okay? So when we study high luminosity object, we also have the opportunity of probing the extreme end of both luminosity function and also the supermassive black hole mass function, okay? But you know, when we talk about luminosity AGN, we mean highly accreting ultramassive supermassive black hole, and due to the existence of supermassive black hole scaling relation, means that also the galaxies are massive, okay? So when we study high luminosity object, there is a lot of relation, and it's also important for the study the evolution of the massive galaxy. And there are also AGN wind scaling relation that have been predicted, have been observed in the recent year by many papers. I report here the famous paper in the publication of Fabrizio Fiore. This is accretion, the outflow rate as a function of the volumetric luminosity. And so you can observe that the stronger the quasar, the stronger is the X-ray wing. So the wind, sorry. So again, study high luminosity objects also means study the AGN feedback at its best. So I show here two recent results involving the helium-2 line. The helium line is a very interesting, it's a very interesting feature because it's a UV line with a large ionization potential in the extreme ultraviolet. So basically means that we have a clean measure of the number of photons in a region which is very difficult to observe. Okay, so the first one is basically the Baldwin effect for the helium-2. Okay, so there is a decrease of the equivalent width as a function of the ultraviolet luminosity. But also interesting these results because it's a correlation between the alpha X and the equivalent width of the helium-2. So basically means that object with very steep X-ray ultraviolet continuum also show very small equivalent with helium-2. Okay, so it means that this is interesting because when you combine all these results, you are observing that ultraviolet, the extreme ultraviolet, and X-ray are tied together. Okay. Even if they are emitted by distinct physical region, because they are expected to be emitted from the accretion disk, from the warm comptonization corona in the inner part of the accretion disk, and also in X-ray, and also mixing together thermal emission and non-thermal emission. Okay, so the other important thing seems that there is a common mechanism, okay, linking all this together, and this common mechanism is set primarily by the luminosity. Okay. And it's also important when we study the strength of this line, the helium-2, with respect to the strength of broad absorption line winds. As you can see in this plot, basically you can observe that the object with the largest BAL winds are those showing very low value of the helium-2. Okay, so this means again that in this region, I mean the region with high luminosity, the region with a very steep alpha X, is also the region where you can find the most powerful broad absorption line winds. And this is exactly what we have observed. So I show you a comparison between these two samples. The first one is the slow general population of quasar. The other one is the Y-selected quasar with a luminosity 10 to the 47. First of all, we found that there is a larger fraction of broad absorption line winds with respect to the general population. And also we found that the BAL winds are stronger, traced by this vanicity index parameter, and also in case of a high luminosity object, the velocity, the maximum velocity of these BAL winds are larger than the general population of quasar. And I strongly invite you to follow the talk by Giustina Vietri and Manuela Bischetti, which are going to present very nice results on this aspect. Again, let's move to the so-called O3 carbon-4 sequence for a luminosity object. You can see here there is there is the equivalent width of the O3, which is a narrow line, so emitted from the narrow line region. And here is the equivalent width of the carbon-4, which is emitted for the broad line region. As you can see that there are a population of weak O3, weak carbon-4, and strong iron-3 emitters, which has been discovered decades ago in the frameworks of eigenvector 1 correlation. Okay, but let's move in detail into the kinematics of the property of this two line. So first of all, I have to introduce this parameter is the velocity shift, which is the shift of the carbon-4 with respect to the systemic ratio derived by the optical spectroscopy, in particular for the O3. Okay. And this means that dedicated near-infrared spectroscopy is needed to find to discover the systemic redshift in this object. As you can see, this is a very an extreme example of what has been found. You can see that basically there is a large shift between the peak of the carbon-4 and the systemic redshift. And you can see also here there is a huge blue component of the line, which is associated to a strong wind in the broadline region. Okay. So again, we can observe that there is a sort of anti-correlation between the equivalent width of the carbon-4 and the velocity of this wind. So typically, have been discovered that there is a population, the so-called population of weak emission line quasar, with very small value of the equivalent with the carbon-4, showing very large shift, larger than 2,000, 3,000 kilometers per second. Okay, and so anyway, this seems not to be present only in this population of very extreme carbon-4 emitters, but also in a more general population. In particular, when you go to high luminosity, you can observe the same kind of shift, okay, even if you are not so weak in terms of equivalent width of the carbon-4. And if you assume that, as observed, that O3, strong O3 emission is linked also to O3 powerful winds, so winds expected to be on kiloparsec scale. This anti-correlation between the strength of the tree and the velocity shift in carbon-4 means a sort of dichotomy or anti-correlation or a sequence between the presence of powerful broadline region winds and narrow-line region winds, okay? Maybe linked to orientation or ionization. I think that there is also this imply further investigation to understand which is the responsible, or maybe are both responsible this anti-correlation. Oops. Okay, when you go to again, I'll show you the blue shift or the carbon-4. Okay. And here as a function of the UV luminosity, you can see there is a correlation. Again, the most luminous objects are the ones showing the largest blue shift. even larger if you consider this population of weak-line quasar. It's interesting if you divide this population according to the delta alpha x, which is the difference with respect to the well-known anti-correlation between alpha x and UV luminosity. In particular, the X-ray one object, so they are the orange one, seems to be more likely to show this very, very large blue shift in the carbon 4, so winds in the borderline region. Okay, has been found this interesting anti-correlation between in this population of hyperluminous quasar, which is reported by Luca Zappacosta. And you can find that basically there is a strong anti-correlation between the velocity shift and X-ray luminosity. So more or less this object, the blue one and also the star, have the same UV luminosity, but there is a decrease, a scatter of 1 dex in terms of X-ray luminosity as a function of the day blue shift. So seems that faster borderline region wind are present in the X-ray weak and luminous quasar. So there are two possible scenarios. The first one is linked to the MHD-driven winds. You can see that in this case, when in case of weak X-ray, basically the carbon 4 winds can be launched very close to the can be launched close to the inner part of the disk, and so can reach very high luminosity. But when you increase the X-ray luminosity, the over-ionized part region is expanded further, and therefore the winds can be launched in the outer disk, so the winds are much slower. Also, in case of radiation-driven winds, there is an explanation of what we have observed. So in this case, we have to introduce this one, the failed wind due to over-ionization, which is fall back into the accretion disk. Again, this is in case when the X-ray is not so strong. But when there is a strong X-ray, this region of the failed wind is much larger, and again, the carbon 4 winds, the winds from borderline region, can be emitted all in the outer part, so the velocity is lower. So it seems to be that X-ray is able to governing this aspect, but also maybe powerful winds capable of removing material from the disk or affecting the disk corona coupling, and maybe can be an explanation for the X-ray weakness in this object. Oops. So let's move to the final part about the dark side of quasar. And in particular, I want to introduce you this the so-called merger and feedback-driven evolution sequence for luminous object and massive galaxy. So there are at the beginning, gas-rich galaxies will merge together. There are different phases. In particular, there is the obscured phase here. And then the feedback is able to clear out the galaxy and also to quench the accretion on the supermassive black hole. So eventually the early type galaxy, red and dead, appears. So this is the NH versus Eddington ratio diagram obtained for the population log and AGN, which basically means they are Seyfert-like object. Okay, as you can see in this region, there is a so-called forbidden region, or the blowout region here, and this region is unpopulated. Okay, and is set by the radiation pressure, which pushing away the obscuration, no? In this case, because the Eddington ratio, the effective Eddington ratio, yes, is larger, and so again the radiation pressure is able to clear out the closed environment of the AGN. Anyway, this is the situation for low luminosity object. Oops, when you go. Okay, when you go in a high luminosity part, and in particular when you start to observe a red luminous quasar, I mean the one selected from WISE, CHUMAS, EUKIDS, I mean near infrared or mid-infrared survey, you can see that the forbidden region start to be populated. Okay. So this is a comparison. This is the general Sloan population, so the blue quasar. Okay, so this means that only when you go to high luminosity, this part can be populated or appear to be populated. And this is quite surprising because you expect here a lot of radiation pressure, so able to clear out the environment in this object. So the apparent lack of radiation pressure feedback in a luminous object can be explained this way. So there is an initial feeding, so increased accretion rate in a very obscured. Then the quasar, the Eddington ratio is larger than 1, the effective one. So start the so-called blowout phase. In this case, okay, you're right. In this case, the quasar start to be blue, okay, because it's swept away the obscuring material. And also the final phase here is on an obscured object, but also the feedback is effective in quenching the subsequent accretion, so there's the fading out region, okay? So the luminosity of the quasar start to significantly decrease, okay? So the explanation why we observe here this population of ear-selected quasar, maybe that short time scale in case of high luminosity object, both blue or red, but maybe in case of red type 1 object, the dusty gas is more spatially extended, so there is a region maybe linked to merger, okay? And so this takes a long time scale to clear out, and this is exactly the region why we observe this one populated, okay? Okay, so, sorry. So summarizing, study the most luminous quasar is important. No? I show you it's important to probe accretion rate, feedback, and also I want to stress this phase, the dust and shadow phase, which is basically impossible in low luminosity object. So I just put here, like final slide, some perspective for the Italian community. So I try to associate some active or very promising topic in the research of high luminosity quasar, associate to different groups, both university or Indian institute in a different region. Okay, this is just done for upset you. Okay, so it's great, so you can get your attention. So you can see I put here Florence, Roma, Bologna, Milano, and Pisa. But when I arrived to Trieste, found any clear logo. So I put the Bora Wind logo, okay, so, which is the only one I found. Yeah. So about nuclear properties, I think, as I show you, maybe it's important to study the area emission and the corona in high luminous object, because now start to emerge a population with some properties similar to lower luminosity. And also interesting to study the spectral property of Eddington AGN, both in optical, in UV, and X-ray. Here also have to add the Padua, which is very active in this topic. And also it's important to study the interplay between the X-ray luminosity, broad line region winds, UV emission, and whatever. Finally, the study of the feedback. So the golden age of high-fuse spectroscopy with Mu, Eris, James Webb, and also the connection between the broad absorption line UFO in ultraviolet and the feedback mechanism, and also with ALMA environment and molecular winds in this luminosity. And finally, as I stress again, the dust and shadow phase of quasar, which is a key phase in the evolution of a massive, is to be a key phase in the evolution of massive galaxy. I think it's a very interesting topic, and I think in Italy we are a lot of people working on it. So I think the interesting results are coming. Thank you very much.
Thank you, Enrico. Questions?
So I have a comment on the relation that you show between the X-ray luminosity and the carbon four velocity shift that you showed before. So is this luminosity relation, if you go back to the slide, but No worries. So, yeah, that's it. So since you showed the Thiem-Linnet sample, so did you try to put the Thiem-Linnet sample in that relation, or do you think that this relation just holds at these luminosities?
Okay, at the moment we have investigated this relationship just in the brightest end of the luminosity function. Okay, but I think that at this smaller luminosity, I think that the mechanism for launching this such strong wind is not so efficient. Maybe it's very difficult to find a luminosity larger than to the 3000 or whatever in the low luminosity regime. If I remember well, maybe Luca can comment on this. When we try to study this kind of wind in the PG quasar population, okay, basically we didn't find any object with a velocity larger than 2000 or whatever. Okay. Yeah, it's a matter of luminosity. Yeah.
Other questions? No questions? It's time to move on. Thank you, Enrico. We now have Tommaso Treu, estimating black hole mass and the structure of the broadline region from velocity resolved reverberation mapping. Aspetta.
Hello, thank you. It's a great pleasure to be here after some time. And I'm going to tell you about some work that we've been doing to measure black hole masses at a very high redshift. And in the process, we've also learned about the structure of the broadline region. So the idea here, of course, is, as you all know, why do we want to do this? So we started from the galaxy black hole connection, and that led us to learning more about black holes. And the question I was trying to answer for some time is, how do we measure black hole masses at high redshift? And it turns out that there's a technique that is very convenient. It's called reverberation mapping. And it turns out that you can extract a lot of information from the good quality campaigns that people have been obtaining recently. And there's a method that we've been developing that is called caramel. We call caramelization of AGN. And I'll show you some results from that. And I'll show you some highlights. So you all know this. So 20 years ago, it was discovered that most galaxies have supermassive black holes, and for some reason, the mass of the black hole correlates with the properties of the host galaxy. And this is great, but we don't know why yet. And one of the fundamental ways in trying to address this is to be able to measure black hole masses at high redshift, because if we can map the evolution of these correlations with redshift, hopefully we can learn about how these correlations come about. So in the local universe, what people do is, how do I play the movie? No. With this, how do I make it? There's no way to play the movie. It's okay, I think you've seen that movie before. Oh, thank you. So if you want to measure the mass of a black hole, like every dynamical measurement, you need a size and you need a velocity. So in the local universe, people, like in the Milky Way, you can map the position of stars and measure their orbits, and from that you get a very precise black hole mass. In the distant universe, when you're looking at AGN, one thing you can do is measure the motion of gas in the broadline region through the Doppler effect, and then if you have a way to determine the distance between this gas and the black hole, you can determine the black hole mass. And so this is great, but it's not being applied very much at high redshift. Typically what people do at high redshift is they take a spectrum like this one, measure some broad line, and then there's some empirical correlation between the width of the line, the luminosity of the continuum, and the black hole mass that is used to infer black hole mass. So can we do better? And so this has been known for a while. Already almost 40 years ago, Blanford and McKee proposed to use something called reverberation mapping. The idea is that you're looking at a AGN, or an accretion disk, And as time goes by, the accretion disk emissivity varies. It bounces off some gas around it, which is the broadline region, and the broadline region responds with a delay, which is the light travel time between the accretion disk and the broadline emitting gas. And so the mean travel time is measured with the clock, so it can be like a week or a month. We divide that by the speed of light, and we get the mean size of the broadline region. And that gives you the distance we've been looking for, even for an object that we cannot resolve in angles. Then, through the Doppler effect, we determine the velocity, and we get a black hole mass. This has been done for some time now. This is a result from some 10 years ago, where people measure the difference in arrival time between the continuum and the broad line to get the size of the broadline region. Multiply that by the line velocity square, you get something called the virial mass. And then you multiply that by a so-called virial coefficient, which is something that encloses all the unknowns about the shape and the kinematics of the broadline region, and that gives you black hole masses. And now there's a value, fiducial value of 5.5 that people adopt for the virial coefficient based on matching the m-sigma relation of active and inactive galaxies. So this is all great, but what we realized many years ago now is that by doing this, you're throwing away a lot of the information. There's much more information in the data. And the idea is that the information data contain about how the gas is distributed. For example, imagine that the broadline region is just a circle face on. All the delays are the same. So you expect a delta function in response of the broadline region. If it's a circle, you expect a top hat. And there's also information about the kinematics. If the broadline region is expanding, for example, the part that is closer to you will be blue shifted and will have a shorter lag than the part that is away from you that is red shifted. So you can learn about where the gas is, how it's distributed, and how it's moving by looking at velocity resolved reverberation mapping data. So the tricky point here is to try to model that. So we came up with a scheme where we can model the distribution of the emissivity and its motion in a very simple and fast way, and we can do inferences where on a supercomputer we can compare millions of models to light curves and spectral series and get some idea of what the BLR looks like and what the black hole mass is. And so this is more detailed, so you can, I'll skip this. Basically, you describe the distribution of the emissivity with some generic functions that are very flexible. They can go from a sphere to a circle to a disk to whatever. And then you describe the motion of the gas as some combination of circular orbits, outgoing orbits, inflowing orbits. The assumption here is that everything is dominated by the Keplerian potential, and there's negligible effect of radiation pressure. So you develop all this, you combine, and I want to give you some highlights. So number one, this is kind of like what the BLR emissivity looks like for this AGN. We didn't impose this, so the topmost columns, the leftmost columns show the edge-on view, and the second, fourth, and sixth show the face-on view. So the BLR looks kind of like some donuts or disks, seeing mostly face-on, which is, we did not impose, but it's reasonable for type 1 AGN. And then you can see red and blue map inflow and outflow. There seems to be a combination of all possibilities. So it seems like, at least at this level of description, the BLR is kind of like weather-like, we like to say. So there will be some phases where the gases that we capture is going out, some of them when it's coming in. And if we observe the same object at 10 years of distance, the black hole mass is consistent, but the kinematics can change. So it seems that really there is some sort of like weather-like activity in the BLR. And as I said, if we use different lines or we repeat observations of the same object, we get consistent black hole masses. This was from the AGN Storm campaign. We modeled H-beta, carbon-4, and Lyman alpha and get the consistent black hole mass for NGC 5548. And the typical accuracy with which we measure black hole mass is about 30%, which is, this is at any arbitrary redshift. I'll show you, this is a reverberation mapping campaign of a lensed AGN, a redshift 2.8. This was a very special case. The leading image was leading by 2 years. And when we started monitoring it back in 2014, we realized at some point it was getting brighter and brighter and brighter. So we turned on monitoring with Gemini. We took spectra every month for many years. And we were able to do the reverberation mapping campaign at this redshift. and measure the shape of the BLR. You see in the middle, it looks like, again, some sort of like donut seen face on. And you measure the black hole mass, which is 8.25 in log m. And you also get a direct measurement of F. Which now leads me to, I think, one is the most practical application of this work, which is how do we get better black hole masses? We cannot do reverberation mapping campaign of every AGN in the sky, but if we have a way to determine F individually, not as an average of 5.5, but if we have other parameters that tell us what F may be, then we may be able to improve our black hole mass estimates. And so this is a study that recently submitted to APJ, where we show the correlation between this parameter F, the virial coefficient, and other observables or model parameters. And you can see very obviously the inclination angle correlates with the virial coefficient because you're looking at the line of sight velocity, so depending on the inclination, that maps into the black hole mass. But interestingly, I think the most interesting one here is the opening angle. There's also a correlation with the opening angle. And so, which led us to make some hypothesis about what could possibly be going on. Is there some regularity in this BLR shape? And it was nice to be just after the talk where the fraction of type 1 and type 2 AGN was described to depend on luminosity. So we speculated that we see that the virial coefficient depends on black hole mass and on Eddington ratio. So imagine that what's happening is that as you go to higher luminosity or higher black hole mass, you can, in our data, it's the same. The opening angle changes, becomes smaller, so they become thinner disks. Then through a selection effect, since these are type 1s, you have to have less inclination. You can have less inclinations to see them face on. And so you have the driving correlation is the one between opening angle and black hole mass, but then through the correlation, through inclination, that leads to a correlation with virial coefficient. And so these are, the blue points are simulated data, where we have some trend between inclination and opening angle and other parameters, black hole mass or luminosity. And this explains very well the correlation between the virial coefficient and the other parameters. So I did not demonstrate that this is a unique and only explanation of what's seen in the data, but what I've shown you is that there's a way to learn about how to measure this virial coefficient more accurately. And if we can do that, we can suddenly go from knowing the mass of every black hole in the sky with a factor of 3 precision, which is currently what we do with the broadline regions, shapes, line emission properties, to about 30%. And so that's a massive increase in the black hole mass determination precision. And I think that's where we're trying to go, and we're trying, of course, to expand our sample, exploring more of the parameter space to uncover more of these correlations, which will be useful to calibrate black hole masses across cosmic time. So this concludes my presentation. So by doing phenomenological models of velocity-resolved reverberation mapping data, we can measure black hole masses with a typical precision of 30% and learn something about the emissivity of the blood-brain region. Some of the recent highlights from this work include some, say, zoological classification of the BLR morphology that tends to be, broadly speaking, face-on donuts with a mixture, weather-like mixture of inflows and outflows. We have demonstrated that we can measure black hole masses out to redshift almost 3 using this technique. And also we discovered that the virial coefficient depends on inclination, obviously, and perhaps maybe on things like black hole mass or luminosity that are observable. And so this, in principle, if it works, is a way to improve the precision of every black hole mass measurement from single apple spectroscopy across the universe. Thank you very much.
Thank you, Tommaso. 12 minutes sharp. Okay, questions?
You charge a lot,
Yeah.
like Satanic.
Yeah. There is, c'è una domanda qui.
Sì?
Funziona? No. In the case of the lensed objects, do you need a precise lens modeling, or since these are delayed?
No, because what you're looking at is the delay between the broad line region variation and the continuum variations in the same image. So you don't need multiple images. The reason why it was convenient to have multiple images is that most quasars tend to do nothing. So you don't want to monitor a quasar that does nothing. But since you have a 2-year lead time, we knew with 2 years in advance that that quasar was going to become brighter by a factor of several in the next 2 years. So that was the main advantage. We knew we could forecast the future and know in 2 years this image is going to be much brighter. And the other thing is that having 3 or 4 different images, you have more time coverage, you have more time sampling, because you can combine the light curves. And so you monitor for 4 years, but you get a 6-year baseline because you monitor all the images at once. And the time delay between the images is measured very precisely, regardless of the lens model from the data itself. And the magnification doesn't matter because you don't care about the luminosity.
Other questions? I have a question. Another question? Okay.
Just a curiosity, I don't understand if in your maps, the old dots that describe the structure of the broadline region, those were showing the density of the region?
Yeah, it's kind of like a Monte Carlo representation of the emissivity. So the thing we can measure is the light that comes from the gas. So we cannot map directly the gas. So you have to imagine that's a representation of the gas emissivity. So kind of like if you had a picture in H beta, this is what it would look like.
So my question is, are any of these objects that you studied being observed with gravity, or are you planning to do that?
So we are currently monitoring some objects that are also being monitored with gravity. The tricky bit is that gravity is doing infrared. So we're trying to monitor them in the infrared, which is very hard work. So I hope it will work, but I cannot tell you yet. Yeah, that would be obviously the thing to do, to combine gravity and the reverberation mapping work. Yeah.
Okay, thank you.
You're welcome.
So we have Susanna Bisogni talking about the Lx-Luv relation and its outliers in quasars.
Thank you. Okay. Good afternoon, everybody. Today I'm presenting to you the latest results on the sensitivity. Oh, sorry. I talked about the microphone. Okay. So I'm talking about the latest results on the relation between the X-ray and UV emission in quasars, and also about the outliers of this relation. Okay, I'll start from the latest result we have published in the last of a series of works on this topic led by our group, just to give you a brief introduction to the relation. So the luminosity at 2 keV and the one at 2500 angstrom follow a relation that is usually parameterized logarithmically, and which informs us on the tight connection between the accretion disk and the hot corona. The main characteristics of this relation is to be nonlinear, a piece of information that is telling us something about the physics behind the relation, even if we don't know exactly what it is. And the nonlinearity of the relation also implies that we can use it for measuring cosmological distances with quasars, and so this is how Risaliti and Lusso built the first table diagram for quasars, and the last results are published in 2019. Okay, so in the last few years, we have our efforts were focused on selecting those sources representative of the intrinsic emission coming from the accretion disk and the hot corona. So selecting non-absorbed sources in both bands, non-broad absorption line quasars, radio-quiet objects. Even so, we have always used photometric data until now, at least for those samples taken from catalogs. And so this time we decided to go with spectroscopic data in the X-ray band, which actually is also the band in which the observational issues mostly contribute to the dispersion in the relation. So we cross-matched the Sloan Digital Sky Survey 14 data released with the Chandra source catalog, and we yield more than 7,000 sources. And after the preliminary selection in the UV band, in which we got rid of all the sources absorbed and again host contaminated, so no representative of the intrinsic emission from the accretion disk, we were left with, we were left with more than 3,000 Chandra observations for which we performed a fit for each one of them. So in this study, the flux at 2 keV and then the luminosity at 2 keV comes from a complete spectral analysis for each observation. Okay. Along with the data from the CSC2, we also considered data from the Chandra Cosmos Legacy Survey, and specifically more than 800 quasars with ultravista data. And this is the final sample we collected after having selected for absorption in the X-ray and after having cleaned the sample for the Eddington bias. So as you can see, both the sample, the CSC2 and the Cosmos Legacy go up to redshift 4.5, while in our previous works with catalogs data, we couldn't go beyond redshift 3. As you can see here, in this work, the last of our works published on cosmology, where in cyan you can see the data from the XMM photometric catalog that do not go beyond redshift 3. And okay, so after all the selections, we were left with more than 1,500 sources, and so we were able to evaluate in a statistically significant way the non-evolution of the relation with redshift by splitting the sample in redshift bins that are small enough so that the differences in the distance with the same redshift bin is negligible with respect to the observed dispersion in the relation. And in such a case, we can express the relation in terms of the fluxes, as in this plot, instead of the luminosities, and so we can check the non-evolution of the relation in a cosmological independent way, because we are not assuming any cosmological model. Okay, so this plot summarizes the results. In the upper panel, you can see the slope of the relation that is steadily around 0.6 up to a redshift of 5.4, which is an important information from the evolutionary point of view of AGN. So this mechanism is the same not only across decades in luminosities in both bands, but also it holds over a wide redshift range. And also in the lower panel, you can see the dispersion of the relation, and you can appreciate how in the highest redshift the dispersion drops to 0.15 dex, which is a value comparable only with those samples with dedicated X-ray observations. So this result was possible only thanks to the spectral analysis we conducted in the X-ray band. Okay, so with this work, but of course with all the previous ones, we have learned quite a bit about the relation between the two emissions, but still we miss the physics behind it, so the process behind it is still highly debated. And so we are at the point in we are asking ourselves if we are not understanding what is going on by studying the relation, can we maybe learn something from the sources that do not follow the relation, so from the outliers? And in this framework, I'm presenting you this sample that you have already heard about this morning in the talk by Bartolomeo Trifoloni. This sample of 30 blue luminous quasars at redshift 3, that were observed with the aim of populating the Hubble diagram at redshift 3, and so they were expected to follow perfectly follow the relation, but much to our surprise, roughly a third of this sample does not follow the relation but falls below it. And of course, there are several reasons why a source should not follow the relation. First of all, the absorption, as we have already said. But what is happening here is something different, because when checked against the local absorption in both bands, in the UV spectra and in the X-ray spectra, these sources don't show any sign of it. And so we proposed as a possible explanation for the different behavior of this class of object, a different state of the hot corona with respect to the radiatively efficient state characterizing the sources following the relation. And so we call them intrinsic X-ray weak sources. And check also the work by Zappacosta and Laurenti that found similar high fraction of X-ray weak sources in highly accreting quasars. Okay, so when we check for differences in the UV properties of these two samples, we actually found some. And for example, we found a difference in the broad emission lines, hinting at the possible presence of a powerful accretion disk in the X-ray weak population that by depleting the UV reservoir from the accretion disk could actually cause the starvation of the hot corona. And another important information on a possible connection between the physics of the hot corona and the broadline region is given by this relation found between the luminosity at 2 keV and the integrated luminosity of the carbon-4 line. But again, the X-ray weak population do not follow the relation, and so something different is going on in this class of sources, and we need, of course, to understand what it is. So by now, we have examined this problem only at this specific redshift, in this specific sample, but we are now in a position in which we can exploit the statistics available with the sample from the Chandra Source Catalog 2, and so we have undertaken and we are undertaking a few steps in the study of the outliers. So the first one is a comparison, a study of the correlation between the X-ray and the UV spectral properties in the two populations of the X-ray weak and X-ray normal quasars. Of course, in the entire sample with a Chandra spectrum and with the SLU1 spectrum. Also, I have extended the X-ray analysis to the SDSS DR16, and so now our entire sample is composed by more than 5,000 sources with X-ray and UV spectral information. So given the high statistical significance of this sample, we mean to approach this sample with machine learning techniques in order to understand which are the drivers of the differences between the sources in the sample. And finally, we have proposed the observation of the O3 line with Lucy at LBT. For a sample of sources with carbon-4 already available from the Sloan Digital Sky Survey and with the Chandra spectra, of course, at two different redshift bins, so that we could be able to study the interplay between accretion disk, hot corona, broadline region, and narrow line region at the different cosmic epochs, besides studying the X-ray weakness fraction at the different cosmic epochs. Okay, so as the last thing, I want just to advertise the table that is online. In this paper, you can find all the X-ray spectral properties for the more than 3,000 observations that I have carried out. So this analysis is available to everyone. And if you want more details about it, please come and ask me. I'll be very glad to give some more details. Thank you.
Thank you. We have time for questions. Fabrizio.
Thanks, Susanna. I'm not sure I understood exactly this outlier problem. I mean, not all of them are outlier, like half of them, right? Of these sample that,
in this sample, between a third and a quarter of the sample is an outlier. Yes.
So how do? So what is the reason why they are outlier? I thought it was a problem with the selection of the sample, that by definition would show lower X-ray emitting QSOs, right? But if that is the case, they should all be outlier, not 30% of them.
No, say it again.
If the problem, if they are outlier because the sample has been selected to have them weak in X-rays.
No, they have not been selected to be X-ray weak. They have been selected to be very luminous in the UV band, and so they, without any sign of absorption, so they were expected to.
But then why don't you see as many outliers in?
Because they are pretty much luminous, and the fraction of objects that are X-ray weak in such a luminous sample is higher with respect to lower luminous counterparts. But you have outliers also at lower luminosities, but they are fewer.
Not entirely convinced, but that's.
Okay, time for one more question.
Grazie. Questo è il mouse. Okay. Hello, everybody. My name is Marisa Brienza, and for those of you who don't know me, I'm a postdoc at the University of Bologna and the Institute of Radio Astronomy. So now with my talk, I will bring the discussion, let's say, to the large scales, and as I will talk about the duty cycle of AGN jets. And in particular, we know that AGN jets were always claimed to play a major role in galaxy evolution and in the evolution of the surrounding intergalactic medium. And I think that recently, with new observations and simulations, this is really being confirmed every day more. And here on the left, I'm showing you a recent LOFAR image at 150 megahertz, where I think we have studied one of the most complex examples of how complex the AGN jet activity can be. This is a galaxy group hosting an elliptic and active elliptical galaxy at the center, and I would like to to focus on two different aspects of this source. The first one is the recurrent AGN activity. Indeed, you can see the multiple pairs of AGN lobes. And the other one is the complex dynamics of this AGN plasma and, let's say, broad sphere of influence of this AGN plasma, which is much more broad than the simple jet axis, but we can really appreciate the fact that this non-thermal plasma is expanding over scales of hundreds of kiloparsecs and perturbing the overall environment. And this is, I mean, when I say perturbing, I mean, of course, displacing the gas, creating shocks and turbulence and heating the gas. And on the right panel, you can see that this is also supported by X-ray observations. So, given for granted that AGN jets are important for galaxy evolution, with this premise, let's say, the two key ingredients that we would like to understand more in order to quantify feedback are the duty cycle on one hand and the energy output. Of course, if we combine these two ingredients, we can really quantify feedback. And the duty cycle, unfortunately, is still not completely understood, especially as a function of environment and host galaxy and so on. So, one of the key tools to explore this further are restarted radio galaxies. So restarted radio galaxies are those radio galaxies showing multiple pairs of AGN lobes or jets, and they are really useful tools to expand this further. And this class of source is not at all new, so we are not discovering this now. It's like 20 probably decades that we know this kind of sources, but their detection and their study has always been quite hampered by the observational limitations that now we start to solve thanks to a broad range of new radio facilities, new generation radio facilities at a variety of frequencies, and in particular at low frequencies. And with low frequency, I mean below 1 gigahertz, let's say. Why this frequency is so important? Because at low frequency, we are sensitive to the oldest emitting particles, radio emitting particles, because this is the and this is because this is the synchrotron spectrum of the radio emitting particles, and this is naturally becoming curver and steeper at high frequency with time, so that at low frequency, the low frequency is the sweetest spot where to detect these old emitting particles. So is our best chance to detect very old lobes from radio galaxies associated to newborn jets. And, oops. So when we have low frequency data combined with high frequency data, then we are lucky enough to be able to apply the spectral age technique. So to study, to determine the radiative age of this plasma, of these particles. And here in particular, you can see a spectral age map. So what does it mean? This is colored by radiative age of the particle populations. In particular, you have to imagine that each point, each pixel in this map represents a radio spectrum, as you can see on the right, and is obtained, of course, by combining different images at different frequencies. And this spectrum is fitted with radiative evolution models and gives us an estimate of the age of the particles emitting in that region. So, for example, in this case, we have an FR2 radio galaxy, so a typical radio galaxy with hotspots. So the particle acceleration actually happens in the hotspots, and this is why the youngest population of electrons are located at the edges of the radio galaxy. And of course, this technique, when applied to restarted radio galaxy, is even more powerful and useful because we can constrain not only the age of the active galaxy, but also infer the duty cycle by estimating the ages of different structures of the source. And this is what we have been doing in the last years. We have been doing this in-depth analysis of individual radio galaxies. And here I'm showing you a couple of them. One is MS0735, which I'm sure most of you know. It's a very powerful radio galaxy, probably one of the most powerful in the nearby universe. And it's sitting at the center of a very massive cluster. The other one, 3C388, instead is an intermediate luminosity radio galaxy and sitting at the center of a rich galaxy group. And in both cases, we managed to acquire multi-frequency radio observations and to perform spectral age analysis. And in both cases, we observed that an active phase of around of the first. So the duration of the first phase of activity of around 50 megayears, and followed by a very short inactive phase of about 10, 20 megayears, and that followed by a newborn jet. So what we see is overall a very quick duty cycle, which might be consistent with this idea of a self-regulated feeding and feedback loop, since both sources are at the center of quite rich environments. And another source which is very interesting in this respect, which we have been studying recently, is NGC 507. This is also an elliptical galaxy sitting at the center of a rich cluster, and its radio emission, so the main double lobes were already known in the literature in the past and were classified as remnant lobes, that is, lobes associated to AGN activity, but without current active jets, so activity from the past. Now with low-power observations, again at 144 megahertz, we have discovered some further emission, which I'm not sure you can see now with this light, but it's here at the bottom right. So this very low surface brightness filamentary emission, which is actually connected with the double lobes, and it's shifted with respect to the host galaxy. Oh. Did I do anything? Okay, thanks. So this newly detected emission, very faint and connected with the double lobes, we interpreted as a remnant AGN emission from a previous phase of a jet activity. So also this source can be classified now as a restarted radio galaxy, let's say. And also for this source, with followed up observations, we managed to study the spectral index distribution and the spectral age, perform a full spectral age analysis, and we derived that again, its duty cycle. So we derived that the age of the newly detected emission is about 300 megayears, and it was produced by a jet activity of duration of about 30 megayears, followed by an inactive phase of about 150 megayears, and then another active phase of 100 megayears where these double lobes were created. One interesting aspect of this system is the co-spatiality between between this newly detected remnant emission and the X-ray surface brightness distribution, which you can see here, and this is the X-ray emission of the thermal surrounding intragroup medium, which has a typical spiral morphology, which is typical of sloshing. So what are we suggesting is that this remnant plasma is currently in this position, and also these filamentary features, which are co-spatial with the arc-shaped features in the X-ray distribution. This is suggestive of the sloshing motion transporting the non-thermal plasma away. So this plasma will probably be spread all around in the next million years. There is some problem with me. Okay. So this is almost the final slide. So my last point is that, as I showed you, with multi-frequency radio data, we can really do an in-depth analysis of these restarted radio galaxies, getting the duty cycle, and also understand when X-ray observations are available, understanding the interaction between the radio plasma and the surrounding thermal plasma. But the next step, the challenge, is now to create big samples of these sources and to study them more statistically, to study their relation with the environment, with the host mass, as I was suggesting before. And one of the key instruments to do that is the low frequency survey, LOTS at 150 megahertz, which we are using to select samples of these sources. In particular, I'm referring to this work by Yurlin, where we selected 158 radio galaxies in different phases of their life cycle, and in particular, out of these, we selected 23 restarted radio galaxies using different selection criteria. Which is about 15% of the population. So now it would be interesting to focus on these restarted radio galaxies and trying to understand their properties. What we can say up to now is that only 4 of these are in clusters, suggesting that not only in rich environments the duty cycle can be quick, and we don't really find any difference in the host galaxy properties with respect to the active galaxy, parent active galaxy sample. Of course, the next step would be to acquire multi-frequency data of these sources to expand their study and to investigate the ages. But this is something that is still complicated and challenging on large numbers, and will be a task for the SKA. And with this, I leave with my conclusions. So my points are that to understand AGN jet feedback, we need, on one hand, to understand the energy output, but it's also very important to understand how much time, for the duration and how frequent is the jet activity happening in various categories of galaxies at different redshift and environments. And restarted radio galaxies can really give us some information on this. We have hints that radio galaxies at the center of massive systems go through quick duty cycles, but this is not always the case, and we need to understand why through the analysis of big samples. And finally, disclaimer, so my work and this talk are mostly based on samples of large galaxies, so hundreds of kiloparsec scales, but these are just the tip of the icebergs or the height of the jet population, AGN jet population. So we also need to go and check the small scale jets, which are the majority of the sources and play a crucial role in galaxy evolution. Thanks.
Questions? I have a very quick question. Since there are no questions from the room, in the extended emission that you are showing in that galaxy, you are talking about sloshing, but I didn't understand, is it the jet which is oscillating, or is it the galaxy which is moving? with respect to the...
Can I go back 1 second? So here, I think, so this part here, so of course we cannot follow it, so we don't know exactly, but the co-speciality with the non-thermal plasma, these non-thermal bubbles tend to rise buoyantly in the intragroup medium, intracluster medium. So this for sure is one phenomenon occurring on this plasma, and on top of that we think that the co-speciality with the sloshing spiral, let's say, is suggestive of the fact that the thermal gas is moving, is sloshing in the group potential well, and it's transporting with it the non-thermal plasma, which is located there.
Okay, thank you. So let's move on because we are starting to be late. Thank you. Next speaker. Elena Bannikova, Dynamical Model of Obscuring Clumpy Tora in AGNs, Interpretation of Amal Observations. I will tell you when you have 3 minutes left. And now I'm putting your talk.
So, buongiorno. I will talk about simulation of dusty torus in AGNs. And you can see here, I'm from Kharkov, from Ukraine, and this is my home university. This is my collaborators with whom we are doing our job. Some of them also from Ukraine. And already today you could see the popular pictures about unified scheme. So the idea that AGNs has the same engine, but the differences between AGN 1 and AGN 2 are explained by different orientation of the torus relative to an observer. So this toroidal structure exactly is interesting for us. And I also would like to say that it's great that now we have a velocity map from ALMA observations, so we can really investigate what has happened in the toroidal structure. And especially to estimate the mass of supermassive black holes for CFR2 galaxies, for example, because in this case the central engine is hidden, and we need to investigate this motion in torus. What we are doing, we consider in-body simulation of the torus, which consists of 100,000 clouds. It's enough for us because it's exactly the number of clouds which satisfies the obscuration effects. So in one line of sight we need 10 clouds, and on the some angle we need a few clouds. Also, we consider it different simulations with a mass of the torus from 1% to 10% of the supermassive black hole. By the way, of course, we are far from the gravitational radius, so we treated supermassive black hole as a classical point mass. About initial distribution, we consider such a way that all orbital elements of the clouds are chosen randomly. But there is some beacons in which clouds are absent. This is just a simple simulation of presence of the wind from AGN, from the central engine. So, and after this, we solve equation of motion using softening parameter, of course, Plummer potential. And in this case, we consider these points not like a point, but like a cloud with some relative size epsilon. And we are using our algorithm, high-order Hermite integration with GPU. And finally, here you can see the evolution of torus cross-section. So this is a problem about searching of equilibrium cross-section of the self-gravitating torus, which is located in the gravitational field of the central mass. So you can see that from the beginning, this is exactly the central mass in the 0, 0 coordinates. So we can see that in the beginning we have initial condition. And after this, we can see that the torus cross-section is changed very strongly. But finally, this is cross-section. You can see that the torus stayed geometrically thick, which is important for unified scheme. And 50% of the particles in the center of torus cross-section, which a little bit shift to the center of supermassive black hole. So we know coordinates. We know velocities of each clouds, and of course we wanted to build the velocity and dispersion maps and coincide it and look for interpretation of the ALMA observation. Sorry. By the way, this is, you can see that of course we check some parameters due to simulation, and when we say about equilibrium state of the torus, it means that the cross-section of the torus doesn't change, the shape of cross-section doesn't change. Of course, here the sizes of the clouds are exaggerated because they should be less, but this is in principle 3D distribution. What is important that of course the dynamic inside of the torus is more complicated than in a Keplerian disk. For example, in the outer part, the clouds move with a velocity which is less than the same velocity for Keplerian disk on this distance. And otherwise, near to accretion disk and the whole of the torus, they will move more quickly, more fast. And we need to take into account this. After this, we decided to build the velocity maps and dispersion maps, and we use the following scheme of our algorithm. So in the first, we are using on-body simulation. After this, since we consider each cloud optically thick and they obscure each other, we using, of course, we rotate the torus relative to an observer. After this, we are using ray tracing algorithm. So we launch the beam, and when the beam meets the cloud, we take these coordinates of this cloud and velocity. So you can see scheme here. And we also divide the picture plane on some cells such a way that mimic ALMA resolution. And finally, you can see our maps. This is velocity, some model maps, velocity maps and dispersion maps. So due to this, we found estimation of supermassive black hole in the very famous XIV galaxy, NGC 1068. But I would like to show you this result for another two XIV galaxies. This is observations, ALMA observations, so we can say that the central region is exactly torus. And you can see here the spot, red spot, this is region with a high velocity dispersion. So this is our simulation. You can also see that there is a red and almost red spots with a high dispersion, which corresponds to observational maps. So what is this? This is emission. We interpret this as the emission of throat of the torus. So and we found the masses of supermassive black hole in these galaxies, and also some parameters. For example, this is combination between inclination angle and the relative size of the clouds. Also, we decide to coincide our simulation for ALMA maps and for VLTI, and so to find temperature distribution in the torus. And for this, we simplify a little bit some model. So the idea is the following. We have a clouds in the torus throat, which are under influence of the emission from the accretion disk. And we consider, we assume that clouds are in thermal equilibrium with accretion disk. This is the first. And the second, we also do some simplification. So this is famous Shakura-Sunyaev disk model, this profile temperature. We just consider that we can, instead to consider the accretion disk with this profile, we can consider the disk with effective radius, which has the same amount of energy, and this is approximately 10 gravitational radius. And this allowed us to obtain some expression between temperature of the cloud, which are heated by accretion disk, and accretion rate and radius from the central engine. So also we are taking into account that there is an angular dependence of the flux from accretion disk, and here you can see the map for two cases with smaller clouds and bigger clouds, so 2 times bigger. And here you can see the path, which is, this is for NGC 1068, which has a much more higher temperature, approximately 800 kelvins. And we can say that this path is the emission of the clouds in the Torus throat. So this is correspond to the famous discovery of VLT MIDI of the Torus in NGC 1068, because also there is a more hot path in the center, and this is also coincide with our result for velocity map. And so we also wondered the interesting result, which is related with the counter-rotation of the Torus in 1068. And I just can show that the famous distribution of the low velocity in this Torus. So counter-rotation, it means that the inner part of the Torus near to hole rotate in one direction and outer another direction. And also we can see that masers, there is some asymmetry in distribution of maser spot, the line of the red, and just a few blue masers. And it was idea that this is not real counter-rotation, because it's really complicated, so this Torus can be destroyed due to instability. But this is some effect of wind, influence of the wind, and the orientation effect. So, and we decided to check this idea. So we extract from our simulation, from our distribution, the clouds which are in the Torus throat, near to accretion disk. And after this, we apply the wind. But the idea is the following. To obtain the asymmetry, we decided to apply the asymmetrical wind, the axis of which is not coincide with the axis of Torus symmetry. And here you can see the result. So after this, we of course do the same procedure. So we consider ray tracing algorithm to take into account the obscuration of clouds by each other. And we have some effect. So you can see that this red shifted part of the clouds are located on the blue shifted part. So, and we can suggest, of course, we can, to make our model more complicated, to add rotation, but for us it was important just to feel, can we succeed with this idea? And so we can say that counter-rotation can be a result of acting the asymmetrical wind together with projection effects. And also, if we will extract the clouds which we can see with high velocity, which we can interpret that this is clouds where maser emission appeared. So you can see also that there is asymmetry in the distribution of this high velocity clouds. This looks like the observational data for NGC 1068. And also what is important also that we can see X shape of the throat of the Torus in projection, which is also discovered by Alma. So this is conclusion. Thank you very much. I think I'm already out of time.
Questions? I have a question. because you have seen earlier from the talk by Tommaso that the BLR was looking like a torus, broadline region clouds. Now you have the torus, so it is easy to assume that the BLR is the inner part of the torus, which is within the dust sublimation radius. So have you tried to take your distribution of clouds all the way in and then see what is, for instance, the line profile of the clouds which are within the dust sublimation radius, whether they look like... yes.
Usually we say that the torus end on the sublimation radius. So, but of course it's interesting. So maybe.
Other questions? Okay.
Hi, Helena. Thanks for the beautiful presentation. I have perhaps a naive question. You were showing the comparison between the increased central velocity dispersion of your model with the ALMA observations. Mm-hmm. So I was wondering, can you trust an increased velocity dispersion at the center in the data? Because I would expect beam smearing effects artificially increasing your dispersion.
You mean this one?
Yeah.
Yes, I trust. This is this is the data of which published by Françoise Combes, and yeah.
Okay.
You think no? I don't need to trust.
No. It's just because I can't really. I don't know what is the resolution. So if you're looking to a specially resolved region or not.
No, for resolution it's okay. So the resolution, as I understand, is less than the spot. Okay. So in this case, yes, we can trust.
Okay. Thank you.
We now move on. Marco Berton, a new puzzle, absorbed jets in active galaxies, narrow line Seifert ones.
Does it? Yeah. Okay, thanks for having me here. If you don't know me, I'm Marco Berton from ISO, Chile. I currently work on Muse. I'm a Muse fellow. And if you're wondering, yes, this is me shooting lasers at the Magellanic Cloud. So, let's start with a brief introduction on the... Well, of course, I already... with a brief introduction on this class of AGN that basically everybody knows by now, I suppose. Narrowline Seifert ones, they were identified for the first time as a class in 1985, and then the actual definition came in 1999 when they basically decided that they are, by definition, with full width at maximum lower than 2,000 kilometers per second, oxygen 3 over H beta lower than 3, iron 2 multiplets in the spectra. And of course, if we assume that the broadline region is virialized, then the low full width can imply a low black hole mass. And if we use the black hole mass as a sort of arrow of time, we can hypothesize that low mass objects will eventually evolve into more massive objects, and so they could be less evolved sources that will eventually grow into something else. And some of them, between 5 and 10%, depending on who you ask, can harbor relativistic jets. Some of them are actually beamed, exactly like in blazars. And indeed, they have a remarkably similar behavior to blazars. You can see the typical double humped SED with the synchrotron hump here, inverse Compton. And they show gamma ray emission and so on, all the usual properties that we actually see in blazars. Actually, NLS1s have often several factors that are at play at the same time. First of all, they have, of course, the AGN, but then they can have strong winds, and this can be seen in radio, but also, for example, in the X-rays, in the form of ultra-fast outflows. As I mentioned, they can have relativistic jets. They sometimes can have radio lobes, not all of them, because actually most of them look compact in radio, but some of them do have radio lobes, and they are actually relatively small, so still at the galactic scale. And some of them even are relics, like this one, for example, in which you can see that this emission is probably not replenished anymore by the nucleus because the jet is now pointing in a different direction. Then you actually have star formation, really strong one. In some cases, it's so strong that the radio emission is comparable to that of a relativistic jet, and they can have dust, like polar dust, and something like that. So in conclusion, they are really, really complicated sources. And if you want to know more about this, like, complexness, if that's a word, of NLS1s, you can actually check Emilia Jarla's papers that we recently published. It's a really short, 78 pages long paper that will probably give you an headache, but there is a literature review of some of the most interesting sources, and so it's definitely worth checking out. Now, just to prove once more that they are really complicated objects, back in 2015, and then for a few years, the Metsahovi radio telescope detected flares at 37 gigahertz from some of radio-silent NLS1s. With radio-silent, I mean that these sources had never been detected before at any frequency in radio. And you see here that they show rather fast variability with behavior that is reminiscent of typical flares, and so this probably indicates jet. If you can see the Y scale here, the flux density is of the order of half or 1 Jansky. So they are pretty bright sources, even if they were radio silent before. And more or less 10% of these radio silent or radio quiet, let's say, sources had actually been detected in Metsahovi. So what's happening? We tried to investigate this a little bit further with a VLA, and we decided to observe at low frequencies, below 10 gigahertz. Now, as you can see, Metsahovi has a really poor sensitivity, so we were trying to get much better data to have a better idea. And my expectation at this point was that these objects were like newborn jet, for example, and I was expecting like a flat spectrum and maybe like quite bright emission at low frequencies. And this is what I found. And when I found this, I thought, okay, I did the reduction wrong, and I did it again. And then I got this again, and I thought my laptop is broken, and so let's try on different laptops. And then when we got again the same result, I thought, okay, maybe this is right. All of them are actually pretty faint. Like, these are the typical flux densities, and you really see that they are all like below 1 millijansky, except maybe like a couple of exceptions here. But still, not comparable with Jansky level observed at 37 gigahertz. So the spectrum actually looks like this, when we have this huge emission here, and instead here we have quiet, normal emission, which actually is perfectly consistent with normal star formation emission. And what we hypothesized is that basically the jet emission is actually up here, because we think that these objects have jets due to the flaring activity. And then there is something that is killing this emission, some form of absorption, which can be either free or synchronous self-absorption. And at these low frequencies, we don't see the jet at all. This is only due to the host galaxy. We also thought, of course, that this could be done, for example, to different beam sizes of VLA and Metsahovi, but this doesn't actually seem to be the case, because in this kind of configuration, both the VLA and Metsahovi are basically covering the whole galaxy emission, and we do see that there's nothing indicating jets in the VLA, literally. So, at this point, there was another option that was like Metsahovi was broken, maybe. But then we started observing them with other at lower frequencies, and look what you see here. They have been detected again. And now there are a little bit too many things that have to be broken for this to be incorrect. Also because even Effelsberg at this point has to be broken because, again, we detected them also with Effelsberg. Right now, the preliminary data that we have seem to indicate that this is due to free absorption. And so there is ionized gas which is absorbing the jet emission. Now, if we also look at the X-rays, we see that, first of all, the X-rays tend to follow the radio flares. And so, as we observe in normal jetted AGN, and so this actually looks like exactly a flare of a relativistic jet. And also, you see that we see this feature in the X-ray spectrum, which we have modeled as a worm absorber. And again, this is ionized gas once more. We don't know if this ionized gas is actually the same, which is absorbing the radio, probably not, maybe they're to different scales, but it's still significant that we do see, again, traces of ionized gas. Now, if we look at spectral index radio maps, we see something even more complicated because we see that the core of both of these sources are actually relatively flat. And this may actually indicate that the jet-based is still unobscured, but we are not really sure about this yet. We need more data to actually get something conclusive about this. And also, so basically the scenario that we are proposing right now is this one. There is a jet, probably a small-scale jet, because to absorb the emission from a really large-scale jet, well, that's kind of more complicated. It's really hard. There is a jet moving through the interstellar medium, and the jet head may be surrounded by an expanding cocoon of ionized gas, and this ionized gas is basically acting like the invisibility cloak in Harry Potter, and it's hiding the jet at low frequencies. You can spot a problem here, because in the last 50 years, we have typically used low-frequency radio emission to identify jets. If this is correct, well, we may have jets that we just have never seen before. Now, the idea that a jet is propagating through the ISM in NLS1 is not new at all, because actually we have observed in several sources blue shifts in the oxygen-3 lines coming from the narrow-line region. And we have found that this blue shift is observed almost exclusively among jetted NLS1s. And so probably this is due to the jet interaction. And so we also found that this blue shift in the oxygen-3 lines does not depend at all on the jet morphology and orientation, which may be a surprise, but it's actually in agreement with simulations carried out in which they show that basically the gas is scattered in every direction, and so we actually see outflows basically in every direction, regardless of the orientation of the jet, not only along the jet axis, but also perpendicular. Okay. If you listened to what I said, basically I mentioned NLS1s in the introduction and then I stopped. Indeed, this problem may not involve NLS1s only. For example, one of the sources, when we investigated it carefully, showed signs of obscurity. Phenomena could present themselves, if we have interpreted this correctly, any time that we have enough gas that can be ionized and then hide the emission from the relativistic jet. So, now, to find out exactly what's going on, because we are still really uncertain about the explanation of this phenomenon, we have already obtained quite a bit of data in radio, in the optical, in the X-rays, and I also recently got new VLA time to look for sources like this in the south by observing their high-frequency emission. So it's a totally blind search. Let's hope we will be lucky. And if we find something south, then we will finally immediately trigger like Muse and ALMA observations, because we need to really be sure of what's going on here. And finally, we will also try soon to trigger VLA observations immediately after the flares to have an idea of how these sources behave at all frequencies. So stay tuned, because I think that we will have a lot of work coming out in the next months/years. Thanks a lot.
Thank you. Questions? No, one moment.
And I already understood your question just by the first three words.
No, yeah, I mean, two basically. The first one, how did you discard SSA? And the second one is, how much is the density of the absorption? Whatever is absorbing would be emitting somewhere else, at other frequencies.
Well, okay. First of all, SSA was temporarily discarded, not at all completely, because we need more data to be sure of this, but it's just by the spectral index, the indexes that we measure, which are way too inverted to be due only to SSA, because the free can actually account for, let's say, a spectral index of +4. In this case, we are actually going even higher than that, so we really need a mechanism stronger than SSA, which is like typically +2.5 in terms of spectral index. Also, sorry, the second one was again? The density of the absorbing material, we have made some calculations, and we need something like the Orion Nebula in front of the jet to absorb it. I don't have the numbers exactly like in my brain because we haven't published this. It's just like back on the envelope math, but we have calculated that. It's sort of Orion Nebula, that's your scale. So it's not something completely weird and impossible. I still don't have answers to this.
Yes, did you try to estimate the absorbing column from the X-ray spectrum?
We are going to do that soon. We are probably doing it right now. Patrizia Romano is working on that, on the X-ray spectrum, and she's doing all the analysis.
Okay, thanks.
Can you go back to the method of detection? Is the emission stable or is variable? And if it's variable, what is the implication from the variability?
This one?
Yeah.
It's variable, yes, but it's really hard to determine jet parameters from this because the detection threshold is so high, basically, that we only see the jet when it's a very, very high state. And so it's really hard to reconstruct anything from these observations. That's why we needed more.
Okay, thank you.
We have time for a very quick question. If not, okay.
So expanding on Marcello, can it be variability?
Yeah, but I mean, yes, but it would require variability of the order of like 10 to the 4, 10 to the 5 to explain if that's just, we can go through that in a bit, but it's a really extreme one if it's variability.
Elisabetta Liuzzo, active galactic nuclei with the Event Horizon Telescope.
Hi everyone. First of all, thanks again the organizer for this amazing in-person meeting. I'm Elisabetta Liuzzo. I work at the Istituto di Radioastronomia in Bologna. I'm part of the Italian Alma Regional Center node there. I'm also the member of Event Horizon Telescope EHT collaboration. Here, the other Italian EHT colleague. And on behalf of the EHT collaboration, today I will try to show how the EHT studies could contribute in the AGN domain. All the EHT papers published up to now used observation taken between 4 and 14 April 2017. 8 antennas in 6 countries around the world observed simultaneously at 1.3 millimeter with a very long baseline interferometer technique to simulate an Earth-sized telescope with a final angular resolution of 25 microseconds. Observation in continuum and polarization are done. EHT is growing in the years, adding more telescopes in the array to improve the image fidelity and quality. In the last campaign in 2022, NOEMA, Kitt Peak, and the Greenland Telescope participated together with 2017 antennas. The EHT collaboration is aiming to investigate with unprecedented detail the physics in the very vicinity of the black hole. Its primary goal is to image the event horizon, which is the surface of no return where matter energy cannot escape from the black hole gravity. This is a perfect laboratory also to test the general relativity theory. What in practice is possible is to image the lensed photoring around the black hole shadow, which contain the event horizon. And this ring structure is due to the photon emitted by the hot and high velocity plasma in the accretion disk and or in the jet, which parts are lensed distorted by the strong gravitational field around the black hole. EHT is able to image the black hole shadow of two objects, M87 Sagittarius stars, having the largest angular scale of the lensed ring that could be resolved by the current EHT angular resolution. These two systems belong to the low luminosity AGN, but they are very different objects in terms of black hole masses, accretion rate, intrinsic variability timescales, also type and morphology. Despite these huge differences, the images of the black hole shadow of this object looks very similar. They show similar ring structure. In particular, the ring diameter confirms the general relativity theory, while the acceleration is an indication of a rotating curve-type black hole. In both of images, we can observe some peak in the brightest temperature. For M87, these structures are explained as Doppler boosting effect of the material moving at high velocity coming towards us. And the asymmetry in the north-south direction in the emission is interpreted as a clockwise rotating black hole. On the contrary, for Sagittarius stars, this structure, this peak, and in general, the distribution of the emission in the ring is not well constrained. This is due to the intrinsic variability of the source on time scale is shorter than the length of the HT observation. And these variability issues also require very peculiar imaging processes and model fitting that require years to the collaboration. Some information on the black hole shadow in polarization are also available for M87, not yet for Sagittarius stars. From this data, important constraint on the magnetic field structure could be retrieved. In particular, for this object, the poloidal magnetic field seems to explain the structure observed. The polarization is also detected and interpreted as due to Faraday rotation internal to the emission region. Electron density, magnetic field strength, and electron temperature could be derived. However, HT higher frequency studies are required to better distinguish the contribution of the Faraday rotation along the line of sight and the underlying magnetic field structure. EHT aims also to unveil the AGN accretion physics. Two general relativistic magnetodynamical simulations are used in the EHT studies, the so-called standard and normal evolution assay, which involve low magnetic fluxes, and the
arrested disk MAD, which involve high magnetic fluxes. Different simulations are done varying the black hole spin and also the so-called Ri, which is the ratio between the temperature of non-relativistic ions and relativistic electrons in the plasma. For M87, 43 simulations are done, and more than 60,000 snapshot images convolved with the PSF are produced. To select the best model, simulation had to pass several criteria. For M87, for example, 4 criteria were used that are reported here in the 4 last column of this table. One criteria is coming from the size and the shape of the image in the HT data, and the other 3 are coming from the multiband observation, in particular X-ray luminosity and volumetric jet power. With some exception, for the M87, most of the same model fail and a large fraction of MAD model passed. Once the best model are identified, it's possible also to retrieve information on where the millimeter photon originates. As this figure shows, more the Ri, the ratio between the temperature of ion and electron, is low on the left panel here, and more the photons are located in the disk plane. More Ri, especially for sane model, is high, and the photons are located more in the funnel here. For Sage, very sensitive. For Sage stars, a simulation had also to vary the observer inclination versus the disk spin, being not constrained by the presence of the jet, like in the case of M87. Here we can see how should appear the ring in case of phase-on disk and edge-on disk. Also in this case, the spin vary, and simulation vary also the Ri and also the magnetic flux to produce a MAD and sane simulation. Then the size observed in the HT images exclude some simulation, like there. More selection is done, it's very sorry about this. More selection is done using the shape constraint always from the EHT image. Even more using the constraint coming from the spectrum, so the set information, multiband observation of the source. And finally, I can imagine this. And finally, using the low frequency size at 86 gigahertz, all models except MAD model with low inclination and prograde spin are excluded. So we are thinking that we are looking at edge-on disk with the spin in the same direction of the black hole spin. Okay. AGN jet is also, HT is also trying to unveil some physics of the AGN jet. This is a schematic representation of a relativistic jet where 4 regions could be identified. The first region, the launching region, characterized by strong magnetic field, large opening angle where the jet originated, and extend up to 100 Schwarzschild radii. Then there is the acceleration and collimation region that extend from 10 to the 3 to 10 to the 5 Schwarzschild radio, characterized by opening angle that decreases and the magnetic energy that converts into the kinetic energy. The following region is the kinetic flux dominated part that extend up to 10 to the 9 Schwarzschild radii, and where the jet is matter dominated. In this region, shock and plasma instability could develop. At the distance more than 10 to the 9 Schwarzschild radio, jet disruption and the formation of the radial lobe could occur, and the kinetic energy converts into the radiation. EHT is able to constrain and to give information on this part, so from the launching to the kinetic flux dominated. Concerning the edge jet launching, two models are frequently are proposed. Is the model that imply that the black hole launched the jet, and the other that the disk launched the jet. From the EHT data for M87, and also thanks to the multi-band constraints, it seems that the jet is in agreement with the Blanford and Znayak jet, so jet launched by the black hole. I can skip this. Result with the HAT data are also published regarding Centaurus A, which is the closest radio galaxies. Studied the low luminosity AGN, and in this case, HT data can probe region about 100 Schwarzschild radius. So we are looking into the launch region of this object. The source appear in the HT image highly collimated, and here, and also asymmetrical edge brightened, and a faint counterjet is detected. The structure resembles a lot to the structure observed in M87 here, but also, for example, by Gabriele in 3C84. So future modeling is required to understand if this jet sheet emission is typical for this kind of object, and also how to model if helical magnetic fields are present or rotating the jet. Also, EHT observed and published results on 3C279, which is an archetypal blazar with flux varying over the entire electromagnetic spectrum. And in this case, the HT data can probe a scale around 2,000 Schwarzschild radius. So we are looking into the acceleration and collimation part. In this case, the HT imager can help to locate the core, which is in this substructure here. These elongation observed in this component are interpreted both as a result with the jet base, but also as a plasma instability or a site of magnetic reconnection, large-scale reconnection. During the HT observation, this source is very variable in gamma rays, and also some variability is observed in the EHT image itself. So follow-up, taking account of both the EHT data and the multiband data closing time are in progress to better understand this source. The source is observed in 4 days, and looking at this source, some proper motion of the jet component are detected here, and they are consistent with traveling shocks or instability in a bent, possibly rotating jet. So these are my conclusions. Stay tuned because more results on EHT will come in the next year. And multi-band, possibly simultaneous campaign are very fundamental to constrain the EHT observation result and simulation, also to obtain a complete picture of the underlying phenomena of this object. In this sense, Marcello Giroletti in the next session will present interesting data on M87 in multi-band view. And stop. Thank you.
Thank you. Questions?
Okay. So I have a question regarding the the axis of the jet. So for Sagittarius A star, the axis is parallel to the plane of the galaxy.
Close to.
The Fermi bubble there's another story.
It's a very good question, and this is a matter of further investigation between, the indication of the bubble seems that the indication should be different, but from the simulation, it seems that it's more phase on disk. So, yeah, but it's a good. We have also to mention that the simulation that didn't take into account some misalignment between black hole spin and disk spin. So maybe also this could explain. Yeah.
Hi, I would ask, considering the two images of M87 and Sagittarius A, is important the effect of the gravitational redshift on light coming from those regions?
Sorry? You are meaning comparing the...
Yes, considering the light that you detected in millimeter bands. So at those distances from the central massive black hole, is it important the gravitational effect of redshift? How much in terms of shift in wavelength?
What I can say is that, we are trying to, I don't know if I'm answering your question, maybe we can go after. We decided to observe this object at millimeter frequency because multi-band observations say that here is the best frequency to where to explore the black hole shadow. And of course, in this at this distance from the black hole, we are in the strong gravitational field. So all what we are seeing is very distorted and by the central field.
Thank you for the nice results from the EHT. I wanted to ask you if for Sagittarius A star, the inclination measurements and spin measurements are actually consistent with what was known from VLTI and stellar orbits measurements.
Up to now, what we found is consistent with those results. There is a caveat, of course, of the inclination of the disk, as also beta arise. But yes, concerning the other observable, the results are very consistent, also in terms of estimated mass and so on. So yes.
Totally independent? And the measurements are totally independent, so it's an independent...
Yeah, of course, yeah. This is also the robustness of our result, also.
I have a very quick question. In M87, you say you find the photon ring, and you say it's a fraction, is a multiple of the Schwarzschild radius, and from that you estimate the black hole mass from the size of the photon ring, if I understood correctly. In Sagittarius A star, you start from the black hole mass and you do your simulations to match the observations. Why is that? Why did you follow the same approach?
No, you mean also, in principle we follow the same approach to estimate the photon ring size. So I don't know if you mean something different, but we start from the set analysis, of course, and also the estimated from other wavelength concerning the central black hole mass, and then derive, in a case of, for example, non-spinning or spinning black hole, the possible size to detect. So, yeah.
Thank you. Thank you. We finished. There is an announcement. First, let's thank the speakers of this session. And then I have an announcement.
So I just want to thank the students from the Liceo Gobetti, which are running out and about here, running with the mic for you for questions. And again, I think we are full for the social dinner, but there are people that express interest but didn't reach us for the payment. So there is no one at the registration desk at the moment. If you want to pay, you have to ask me, and then we can sort it out. But please do so before the end of today, if you can. And we will reconvene at 4:30. No, sorry. How much is 5? 15 to 5. 15 past 5. Okay. 15 past 5.